we're going to talk about some special cases of systems of linear differential equations, that is, those that have repeated eigenvalues and those that have zero eigenvalues. First, let's review some concepts from before about complex eigenvalues. Recall that we denote the symbol I as the square root of minus 1. I stands for imaginary number. If a and b are real numbers, we call a number in the form a plus bi a complex number, and we denote the collection of all such complex numbers by a bold letter C. We say that A is the real part of such a complex number, and we'll denote this by RE. Similarly, we'll denote B as the imaginary part of some complex number, and we'll denote this by IM. We can add and multiply complex numbers in a rather clear way by just simply keeping track of both the real and imaginary parts. If a plus bi is a complex number, then its complex conjugate is a minus bi. Similarly, its norm is the square root of a squared plus b squared. Euler's identity states if lambda is a complex number, that is a plus bi, then e to the lambda t is another complex number whose real part is e to the at times cosine bt, and whose imaginary part is e to the at times sine of bt. Now, in all of this, we've introduced complex numbers and hence complex valued functions, but we really like to focus on real valued solutions. Let's consider now a two-dimensional system, dy dt equals a times y, where our matrix A is a 2 by 2 matrix with two distinct complex eigenvalues, lambda 1 and lambda 2. First, lambda 1 and lambda 2 are complex conjugates of each other. That is, lambda 1 equals alpha plus I beta, while lambda 2 equals alpha minus I beta. Second, the only equilibrium point is y sub 0 equals the origin. Third, if v sub 1 is an eigenvector associated to the eigenvalue lambda 1, then its complex conjugate, v sub 1 bar, is an eigenvector associated to the other eigenvalue lambda 2. Finally, let's say that y sub 1 of t is a straight line solution, which equals to e to the lambda 1t times the eigenvector v sub 1 plus the equilibrium point y sub 0. Then let's let capital Y sub re be the real part of this y sub 1, and capital Y sub im of t be the imaginary part of such y sub 1. Then the general solution to our two-dimensional system is capital Y equals some scalar c1 times capital Y sub re plus another scalar c2 times capital Y sub im. We can put all of this together into an algorithm. Let's assume a couple of things about a 2 by 2 matrix A. First, Q does not equal to 0. Q in this case is the determinant of A, namely AD minus BC. And P squared minus 4Q is less than 0. In this case, P is equal to negative A plus D. We'll use the following algorithm to perform the following steps in order to solve a two-dimensional system dy dt equals our matrix A times y. First, compute eigenvalues lambda 1 and lambda 2, as well as eigenvectors v1 and v1 conjugate. Second, we'll compute the real and imaginary parts, namely capital Y sub re and capital Y sub rm, in terms of a straight line solution, capital Y sub 1, which is e to the lambda 1t times the eigenvector v1 plus the equilibrium point y sub 0. Third, we'll return the general solution, capital Y equals C1 times capital Y sub RE plus C2 times capital Y sub IM. Using this algorithm, we can now list a few definitions. Let's say that our eigenvalue lambda 1 is alpha plus I beta. If alpha is negative, we say that our equilibrium point y sub 0 is a spiral sink. If alpha is positive, we say that our equilibrium point is a spiral source. If alpha is equal to 0, we say that our equilibrium point is a center. The solution, capital Y of t, is called a periodic solution. Its natural period, capital T, is 2 pi divided by beta. Its reciprocal, 1 over t, namely beta over 2 pi, is called the natural frequency, whereas 2 pi over t, that is just beta, is called the angular frequency. Today, we'd like to discuss the remaining cases we haven't talked about yet, namely repeated eigenvalues and zero eigenvalues. Let's consider the following setup. Say that we have a two-dimensional system, which we can express in terms of a 2 by 2 matrix A, namely dy dt equals the matrix A times y. Recall a few definitions. First, an eigenvalue, lambda, is a root of a characteristic polynomial. We can express this now using the quadratic formula in terms of p and q. Recall that the eigenvalues are non-zero if and only if q does not equal to 0, and the eigenvalues are distinct if and only if p squared minus 4q does not equal to 0. Second, an eigenvector v associated to an eigenvalue lambda is a non-zero vector such that a times v equals lambda times v. Recall that if the eigenvalues are real numbers, then we can choose the eigenvectors to be real as well. If the eigenvalues are complex numbers, then we can always choose the eigenvectors to be complex conjugates of each other. Finally, an equilibrium point is a vector y sub 0 such that a times y sub 0 is the origin. On the previous slides, when we did our review, we talked about a few classifications of these various equilibrium points. Here we'll put them all together into one place. We'll classify them depending on whether our discriminant p squared minus 4q is either positive or negative. If it's positive, then this means that our eigenvalues, lambda 1 and lambda 2, are either both negative, both positive, or one is positive and one is negative. If they are both negative, we say that we have a sink. If they are both positive, we say that we have a source. And if one is positive whereas the other is negative, we say that we have a saddle. If either eigenvalue is 0, we're not really sure what to make of this just yet. This is something we're going to discuss today. On the other hand, if the discriminant p squared minus 4q is negative, then we have complex eigenvalues. If the real part of our eigenvalues is negative, we have a spiral sink. If the real part of our eigenvalue is positive, we have a spiral source. And if the real part is equal to 0, then we simply say that we have a center. Definitions, let's consider the concept of straight line solutions. Recall that a straight line solution to our two-dimensional system are functions that are of the form y equals e to the lambda t times v1 plus y sub 0. In this case, the v is an eigenvector and y sub 0 is an eigenvalue. If there are two distinct real eigenvalues, that is p squared minus 4q is positive, then the general solution to our two-dimensional system is a linear combination of these two straight line solutions. On the other hand, if there are distinct complex eigenvalues, then the general solution is a linear combination of the real part and imaginary part of this straight line solution. Now let's put all of this together to formulate some motivating questions. We've seen that if there are distinct eigenvalues, either distinct real or distinct complex, then we have methods of finding the general solution in terms of real valued functions. But what is the general solution if our discriminant p squared minus 4q is equal to 0? That is, what happens if there are repeated eigenvalues? Second, the origin is the only equilibrium point if and only if A is a non-degenerate matrix. We can see from our formulas that the determinant of A, which is AD minus BC, is also equal to Q, which is also equal to the product of the eigenvalues, lambda 1 times lambda 2. So our matrix A is a non-degenerate matrix if and only if both eigenvalues are non-zero. So what are some equilibrium points if Q is equal to 0? That is, what happens if there are 0 eigenvalues? This is what we're going to discuss today. We're going to take a look at these two cases, when we have repeated eigenvalues and when we have 0 eigenvalues. Let's begin with one of two main propositions. Say that A is a 2 by 2 matrix with only one eigenvalue lambda. That is, we have a repeated eigenvalue. Then if we take A minus lambda times the identity matrix and square this matrix, we find the 2 by 2 0 matrix. Let's assume that A is a scalar matrix. That is, it looks like lambda times the 2 by 2 identity matrix I sub 2. Then for any basis of R2, the general solution we can write in terms of straight line solutions. That is, we have e to the lambda t times v1 plus y0 and e to the lambda t times v2 plus y0. These are straight line solutions going through the origin y sub 0 equals the 0 vector. Finally, let's assume that A is not a scalar matrix. Then we have a basis v1 and w1 of R2 in terms of non-zero vectors satisfying the following. A minus lambda I2 times v1 is equal to the 0 vector, and A minus lambda I2 times w1 equals v1. In this case, the general solution we can write as a linear combination of y sub 1, which equals to e to the lambda t times v1, and a new function we haven't seen before, y sub 2 equals e to the lambda t times v sub 1 plus w sub 1. In the latter case here, recall that v sub 1 is an eigenvector, whereas we're going to define w sub 1 as a generalized eigenvector. Let's say a little bit behind why this proposition is true. First, recall that the characteristic polynomial is lambda squared plus p lambda plus q. Since our matrix A has repeated roots, we see that p squared minus 4q must equal to 0. Rather explicitly, if we write our matrix A as A, B, C, D, and if we choose our eigenvalue as negative p over 2, which is the same thing as a plus d over 2, then we simply find that the square of the matrix A minus lambda I2 must be the 0 matrix. Let's go on to the second part of the proposition. Let's assume that A is a scalar matrix. We'll try to write down the general solution by essentially trying to solve a initial value problem. Here, let's write our initial value problem as dy dt equals the matrix A times y, where y evaluated at t0 is some initial value z. Since v1, v2 is the basis for R2, we can find scalars c1 and c2 such that z, our initial value, is equal to c1 times the vector v1 plus c2 times the vector v2. In this case, we can choose the scalars k1 and k2 cleverly so that our function, capital Y, which equals to k sub 1 times y sub 1 plus k sub 2 times y sub 2, is indeed the solution to the initial value problem. And finally, let's consider the case where A is not a scalar matrix, but we still have repeated eigenvalues. I'd like to introduce a linear transformation T that takes a vector V to the vector A times V minus lambda times V. Both the kernel and the range of such a linear transformation must be equal to each other because T squared equals to the 0 transformation. And in fact, both the kernel and the range must be one-dimensional subspaces of R2. This means that we can find vectors v sub 1 and w sub 1 satisfying T of v sub 1 equals 0. V sub 1 can be considered to be a basis vector for this one-dimensional subspace, which is the kernel, and T of w sub 1 equals v sub 1. Putting this together, now it's just a matter of showing that y sub 2, which equals e to the lambda t times v1 plus w sub 1, is indeed a solution for our two-dimensional system. Now let's consider what happens when we have a 2 by 2 matrix A that has a 0 eigenvalue. In this case, let's say that lambda sub 1 equals 0, and let's denote lambda sub 2 as the other eigenvalue of A. First, let's consider the case where lambda sub 2 does not equal to 0. Then our matrix A has distinct eigenvalues, so there's a basis y sub 0 and v sub 2 of R2 says that A times y sub 0 equals the 0 vector, and A times v sub 2 equals lambda 2 times v sub 2. Notice that y sub 0 really is just an equilibrium point, but because one of our eigenvalues is lambda 1 equals 0, we can also view this as an eigenvector. The general solution now to our two-dimensional system is a linear combination of straight line solutions. The first, y sub 1 of t equals y sub 0. This is our equilibrium solution. And the second, y sub 2 of t equals e to the lambda 2 times t times our eigenvector v sub 2 plus our equilibrium point y sub 0. And finally, let's consider the case where both eigenvalues are equal to 0. That is, lambda sub 2 is equal to 0 as well. then this simply reduces back to the previous case that we had before when we have repeated eigenvalues. As a quick remark, notice that the solutions y sub t will behave very differently depending on the sign of the second eigenvalue. That is, whether lambda sub 2 is negative or lambda sub 2 is positive. We'll see this next as we discuss some examples. Let's first consider an example where our two-dimensional system will be associated to this 2 by 2 matrix, -5, 1, -1, and -3. We see here that the characteristic polynomial is equal to lambda plus 4 squared, which means that we have exactly one eigenvalue. Let's write this as lambda equals -4. We can actually determine an eigenvector as well as a generalized eigenvector by writing down the two equations that you see on your screen. A minus lambda I2 times V1 equals the zero vector, and A minus lambda I2 times W1 equals V sub 1. There are many choices of V sub 1 and W sub 1. In fact, there are infinitely many. But we simply choose two non-zero vectors where both of these equations hold. Then the general solution we can write as straight line solutions in terms of y sub 1, which is e to the -4t times the vector 1, 1, and y sub 2, which is e to the lambda t times v sub 1 plus w sub 1, which we can write as e to the -4t and the vector t plus 1. Note that all solutions, that is, as time increases without bound, must tend towards the origin. We can actually see this once we plot out the phase diagram and the direction field. Here, the straight line that you see is the line corresponding to the eigenvector v sub 1. This is the vector 1, 1, if you recall. Now you can see that all of the solutions are spiraling in towards the origin. In this case, the blue dot is the equilibrium point 0, 0. So we do see that all solutions here do seem to spiral inwards towards the origin. Now let's consider the following two-dimensional system associated with this 2 by 2 matrix, namely -3, 1, 3, and -1. The determinant in this case factors as lambda times lambda plus 4, which means that we have two eigenvalues, namely lambda 1 equals 0 and lambda 2 equals -4, corresponding to an equilibrium point 1, 3, as well as the eigenvector -1, 1. We can then see that the general solution we can write in terms of straight line solutions will be what you have here on your screen. It's a constant minus k sub 2 times e to the -4t, and then -3 times the same constant plus k sub 2 times e to the -4t. We can see here that all solutions, y is t, tend to a scalar times y sub 0. That is, as time increases without bound, we see that capital Y sub t tends to k1 plus k2 times the vector 1, 3. This means that there's actually an entire line to which our solutions tend to. Here's a plot of the phase diagram and the direction field. You can see that all of the arrows are not really tending towards one point, but actually they're tending towards this gray line. They're tending towards an entire line. This line here is a plot of the direction that we find from our equilibrium y sub 0. Thanks very much for watching.